And then after, when you will send slides, we will upload slides.
Okay.
Okay. Okay, let's start. Hello, everybody. Today, we have a pleasure to have a talk by Professor Pisin Chen. He will tell us about black hole information loss paradox and the Unhell experiment, analog black hole evaporation via laser. This is the name of an experiment, but Pisin Chen will tell us all these details. Please, 1 hour.
Okay, thank you very much. Yeah, thank you all for very much for the invitation. This is my great honor and pleasure. So today, considering the nature of the audience, I think, I suppose, mostly theoretical oriented. So I would spend, a good fraction of my time motivating you from the theoretical side with some update on the recent developments of the solutions to black hole information loss paradox, and then turn my attention to the proposal of an experiment that may possibly shed some more lights on this debate through experimental means. So here, let me go ahead, and this, I'd like to pay tribute to Stephen Hawking. We all know that this topic has a lot to do with him. Let me see if I can make this, screen more, yeah, here we go. All right. This is a figure I stole from Hawking's famous book. And so the argument, of course, heuristically arguments based on his, his point of view. Now, this part we all know already, all of us, that by fusing general relativity, black hole solution with quantum field theory, Hawking made a seminal discovery in 1974-75 to find out that to have found that the black holes are not entirely black, but it will radiate. And this radiation will result in the reduction of black hole mass, and therefore it's apt to refer it as an evaporation, because the black hole, by emitting radiations, will reduce its mass until the end, whether it's entirely disappeared or leave behind it a remnant. That's a subject of debate, but not not the focus of today's talk. Now, Hawking found that this evaporation of the black hole is black body in nature and associated with a temperature, which we now call Hawking temperature, and that involves, and as shown in this red box, with that the temperature is inversely proportional to the black hole mass. The rest are all constants: Planck's constant, speed of light, Newton's constant, and this 1/8 here. Now, if one regroup the constants, and one can in principle write it as h bar g over 2 pi c, where g is the gravitational acceleration at this, at the event horizon, at the structural radius, gm over rs squared, where structural radius is like this. Now, I think it was maybe a year or some later, Hawking suggested that this temperature can be heuristically derived by simply invoking the Heisenberg uncertainty principle. And then you argue that vacuum fluctuations with the inverse of its energy, the wavelength, de Broglie wavelength or something, the size of the fluctuation, if it is of the order of the Schwarzschild radius, then the black hole cannot clearly confine that fluctuation, and this fluctuation may escape. And by doing so, one can recover the expression of this temperature, say other than this 1/8 pi, and you can recover the rest. But this is just kind of help us to appreciate the nature of this radiation heuristically. Now, whenever we see a physical formula that in one stroke connects many fundamental constants, such as this one, there's the Boltzmann constant on the left side, Planck's constant, Newton's constant on the right side, and C, you may even call it Einstein constant, but it's the speed of light. And this involves naturally on the left side. This is, symbolic of statistical mechanics. On the right side, there's the quantum mechanics or quantum field theory. And with a G, there's the gravity or general relativity. So a simple formula as this that connects quite several important fields in physics in one stroke. And so this definitely deserves further look into it. There may be more, more secrets hide behind. Now,
can I ask you a question?
Yes.
Let us look to the Hawking formula for the temperature. When the
Sorry?
mass goes to zero, the temperature goes to infinity. What do you think is infinite temperature?
Right. And that that is an extrapolation, shall we say, because this derivation was based on semi-classical approximations, meaning that Hawking, which is all justified when the black hole is astrophysical size black holes, the Hawking temperature, since it's inverse proportional, the Hawking temperature is extremely low, small, and therefore it is justified to ignore the back reaction, and you can safely treat the space-time geometry as a background without worrying about its back reaction. And this is fine when the temperature is low, and therefore the typical energy of an emission, let's say it's a photon, the typical energy of an emitting photon is so much smaller than the mass of the black hole, and so you can ignore the higher order terms, and this is fine. However, when the black hole is evaporating down further and further towards the Planck size, Planck mass, then the temperature is rising up to Planck temperature. And then there's the problem, because any typical emission at Planck temperature of a black body will be of the order of the Planck mass. And therefore, this emission takes away an energy which is comparable to the emitter, to the black hole itself. And so this semi-classical approximation is not valid. And therefore, Hawking's claim that this evaporation towards the end will result in the total disappearance of the black hole, which is a conclusion by, as you just commented, pushing m to 0. But that we already knew is not physical because t goes to infinity. And as I also further explained, theoretically, this is not justified. So that is already in the domain of quantum gravity. And so I think it is inconsistent to push this to the limit of mass goes to 0.
So for small mass, the Hawking formula is not true, and there is no information paradox.
Why?
Because to get information paradox, we have to get a complete evaporation. Right?
Yes and no, but I'm glad that you comment on this. It happens that my co-authors and I had published a rather thick review article in Physics Reports, I think in 2015, with the title exactly as the information loss paradox and black hole remnants. And this is kind of it really takes another seminar to deal with this black hole remnant issue, which I proposed in 20 years back. And that one, yes, has some pitfalls and some implications about information loss paradox. And if you are interested, please go take a look of that article, which is pretty big. And in that article, we review up to then most of the proposed solutions to information loss paradox, and also added about the considerations if the black hole never actually evaporated down to 0, but leaves a inert remnant at the Planck mass and Planck size, and what would that imply to the information loss paradox? Indeed, one can imagine, for example, John Wheeler's bag of gold type of geometry, space-time geometry. So as long as you still have some part, of the black hole, state, without further evaporating, then there are quite some options, some possibilities opened towards this information loss paradox resolutions.
But
okay.
The title of your today lecture reads information paradox. Probably you will explain what do you mean information paradox, right?
I think I will. Let me see if
Thank you.
Yeah, I will. I think I will. Okay, thank you. So well, here's a pictorial kind of definition or explanation. So what it says is, presumably black hole has a lot of information, even from the Bekenstein-Hawking's point of kind of entropy's point of view. So there's the black hole has a thermal entropy, which is proportional to its surface area, as we have all learned. And then that's a Bekenstein, entropy. Now, when you evaporate, this is black body, and so it's essentially heat, just at different temperatures, and so gradually the black hole shrinks size, and you have more of the original mass now permeating in space in the form of black body, thermal radiation. So let's say, and let's put this black hole remnant issue aside. Let's say, following Hawking's original argument, now your black hole eventually disappears, and then the whole universe is filled with heat. But heat doesn't have a lot of information. It's just purely random. And so the question is, where did the information go? And you can ask, what's so important if the information is lost? That is that's the philosophy of Bill Unruh and Bob Ward. They believe they argue that even if it is lost, there's no big deal. But let's say on the other camp, the other camp feels that since quantum mechanics, quantum field theory, one important tenet of quantum mechanics and quantum field theory is the conservation of probability, or unitarity, so-called. And so this is a big deal if it is indeed lost. Now, so one prime suspect about, let's imagine if we want to keep track of the information. Now, one prime suspect is the Hawking radiation, whether they actually carried away some information, and if so, then how? Now, as I just now mentioned, this was whether this black hole evaporation will result in the loss of information was first pointed out by Hawking himself in 1976. And as then in the
On it.
hello, just a second, okay, and there's been endless debates ever since. Relatively more popular or frequently discussed ideas includes in the 1990s, Susskind and co-authors, suggested the idea of black hole complementarity, but that idea was facing some challenge in the year 2012 by 4 and 5 authors, including Joe Pociński, and this is by the name firewalls, as many of us have heard. And then there's this, I feel, quite important development. First, to my knowledge, first suggested by Frank Wilczek in 1987, and then, but strangely, he, that work of 1987 was in a, I think, Texas symposium or whatever proceedings. The formal paper was done with his students in 1993, 92, I forgot. Yeah, now took quite some years. And Unruh and collaborators and had some follow-up in this direction. So the attention moves to the entanglement between Hawking radiation and its partner particles. Then, as I just now mentioned, my co-authors, Yenchin An and Donghan Yum of Korea. Yenchin is currently on the faculty of Yangzhou University, and myself, this was in Physics Reports 2015. And so this can be a solution to the problem, to the challenge. Then, and also, I think a year later, Don Page, Misao Sasaki, and the three of us together, we wrote a paper to argue against the firewall conjecture. Again, I mean, with the interest of time, I cannot jump too deep into. Please, if you are interested. Then, as many of us have noticed, this in 2016 until the 2018 when Hawking passed away, the three authors here published a series of several papers where they suggest that BMS symmetry can, in general relativity, can result in a case of black hole, results in some soft hairs, what they call, and that they suggest can be responsible for preserving the information. You may or may not have heard that very soon, I think in the same year or the next year, Steve Giddings and I think Raphael Bousseau pointed out separately that this so-called soft hairs actually corresponds to some phase shift, which doesn't carry information. And so this was kind of a counter argument, shall we say. So I can down to this point, I can briefly summarize by saying that almost all solutions suggested earlier have some kind of a counter argument, counter example, kind of proposed, and therefore, it's kind of just, stagnating because, there's up to now, I think one can safely say, even with the replica wormholes and such islands conjectures, it's still not a universally agreed viewpoint. So just now I mentioned about Unruh and Wall, where they also argue that there's no firewalls, but also they insisted, and this, by the way, is not their first paper about the topic, that there's nothing wrong with information loss. So this is another kind of interesting point of view. And so just now I already mentioned about this is the rather hot topic from the string theory camp in the past 3 plus minus years, with the idea of replica wormholes, which is kind of closely related to so-called islands conjecture. Now, so from a different angle of approach, my collaborators and I, mainly Misao Sasaki, Donghan Yuan, and in this case also Jungi Yun, we published several papers, which this last bullet I will come back to with a little bit more details in a few minutes. So our approach is from the Euclidean path integral, or you can say Euclidean quantum gravity methodology, and so-called wave function of the universe. So this is a la Hawking, Hartle-Hawking type of approach, if you know what I'm talking about. And there are some interesting consequences. So I'll mention about that later. Now, later we will, I think this is generally agreed that when talking about the conservation, the information, and it's closely related to the concept of entropy. And as far as the black hole is concerned, the Bekenstein entropy is not the only entropy. I hope we all recognize this, and because surely this black hole evaporation, assuming this whole universe just will have one black hole and then nothing else as an initial state, and gradually the rest of the universe, let's call it system B, is gradually filled with the Hawking radiation. But as Schrödinger has taught us, the black hole, the system A, and what it has emitted, evaporated into system B, they are not, unlike classical physics, they're related. They're actually entangled. And I like to quote Schrödinger's statement here. He says quantum entanglement is not just a property of quantum mechanics. It is the character of quantum mechanics. It fundamentally breaks quantum mechanics from classical physics. And to this audience, it doesn't take me to educate. I think we all know that. Now, one feature of quantum entanglement is that it follows the rule of monogamy, and therefore they are in pairs. Now imagine this gray area is system A, the rest is system B, you can imagine that, and imagine these are vacuum fluctuations, and you can imagine that they are kind of the pairs entangled, but the pair may not necessarily be both on the outside like this, or necessarily both on the inside. Sometimes they cross, okay? And so they're entangled. All right. Now, just now, I was asked to define information. So information as defined here, actually, this is taken from down page. Yeah, first let me say S is stands for entropy, and SB/A is the entanglement, the entropy for the entanglement. So it's the subtraction between the two, which is defined as the information. Now, imagine this as a log-log plot. All right, so it's the entropy S versus time, and the black hole's lifetime. So let's imagine that at time 0, the black hole is in a pure state, so there's no mixture, so it's just by itself. Then, of course, this is just kind of a theoretical model. No real black hole can be like that. But anyways, let's assume that this is the initial state, and as time goes, it continues to evaporate, and therefore it gradually turn into a mixed state. The inside and outside can be entangled. Now, if you really want to preserve information or unitarity, then you like to have the final state return to a pure state. Now, so we just now mentioned about system A and outside system B. Now, so let's take a look of the black hole itself, system A. Now, system A has an entropy, which we already said, it's Bekenstein entropy. Let's call it S of A. And at the beginning, it has a full size. It's at the end, Bekenstein entropy is at its maximum. Then as time goes, it evaporates and it shrinks its size, and this entropy goes down. At the end, let's not worry about black hole remnants. So it goes down to 0. On the other hand, the radiation, system B, starts 0 and then gradually, eventually it's all radiation. All right, so that we agree. Now, so by this definition, the information then will be essentially 0, nothing going out, until roughly this black hole mass reduced to about half size. Then there's about half of its initial energy that's now in system B, and the other half remains as the black hole. That actually, or when the two entropies are comparable, that's actually where the entanglement entropy in green reaches its maximum. And this kind of even intuitively can be appreciated. This is when you have the maximum of entanglement. When your black hole continues to reduce its mass, although and likewise on the other side it's the same. Although the entropy of the radiation side keeps going up, but their entanglement is reduced. Okay, so eventually this entanglement goes back to 0. The information then goes the other way based on this. Then you go after about halftime, we call this the page time. The information finally starts to release out and eventually recover to, let's say, 1. Let's normalize it to 1. And so this is the way Don Page, in his famous 3 papers in 1993, describes the recovery or preservation of information. Now, so here we, in this whole business discussing about black hole information, and everybody knows about page curve. This is the page curve, and this is the page time. Now, however, I must comment that this Don Page's work is based on quantum mechanics. There's no gravity involved, all right? And so this is a nice model, but it's not exactly realistic as associated with true black holes. Okay, so this is what I like to comment. By the way, this is a photo that Don Page gave me. And this was, I think, in 2004, when Hawking conceded that he likes to make bets, right? We all know. And so he made a bet with Don Page in the early 1980s when Don was his postdoc. And Don believes that information will be preserved, and he believes not. And by 2004, he conceded, and he said, well, information really will be preserved. I mean, this is just a belief. So the bet was $1 US, and this was a $1 bill Hawking gave him. Too bad that resolution is not very good, but if you have a good eyes, this is not really George Washington. This is a Marilyn Monroe. So Hawking makes a small joke to Don. Okay, now so a little bit of an update about the latest developments, shall we say? Since I'm only familiar with my own paper, and so let me just say what we have done lately. All right, so this is a approach based on Euclidean path integral. I have already mentioned to you, but what's new was we posited that path integral, you can have many different paths. So the outstate has it's this summit, it has many different final states you can sum over. But what we posited or assumed is that what happens to this universe is that there are at least one information losing history, and also at least one information preserving history. Now, in the formulation of Euclidean quantum gravity, there's the allowance of tunnelings between different histories, and you can call it instanton, etc. Now, so therefore, when one goes through the details, one will find that what happens is that the information preserving history is the final destination. So the history always turns to the one that preserves the information. And at the beginning, it was in the information losing side. Let me use this diagram, which may be better. So you begin, your black hole begins the evaporation. By the way, in this approach, we Euclideanize the time. So as you certainly know, so this is eventually you have to turn back to the Lorentzian space-time. Now, so what we're saying is that there are multiple histories, and that's exactly what just like Feynman diagrams, Feynman path integrals. There are many possible histories, and furthermore, there can be, in principle, tunnelings or jumping across between different histories. And this is definitely allowed in the formulation of Euclidean quantum gravity in the form of instantons tunneling through. And so it's an assumption, and I like to make that loud, that the final destination follows the information preserving. So this is really not a proof that the information is preserving, but more about how was it preserved. I wish to make this clear to the audience. And so for those who are familiar with Penrose diagram, and so this is what we are saying. This is more of a standard, there's a, infalling star forming black hole. This is the black hole event horizon. And where's the future infinity? There should be some wiggles and so on. Now, but under our conception, we say that when you're forming your black hole, and there are from time to time there are tunnelings, and when this happens, it doesn't really fall into eventually the space-time goes this way, and therefore you don't have singularity anymore. You recover the information. And so let me quickly summarize what I'm saying. So first, we assume that, and this is, I think, quite justifiable, there are multiple histories, just as as consistent with the Euclidean quantum gravity. Then, but this second assumption, late time dominance of the preserving history, is an assumption, no hiding, and these conditions give us a clear description about how things happen. You can even draw a Penrose diagram for that. And now, so this is again taken from our recent paper. So there, the information losing history, and the entropy is just going down, and then I should say probability of a particular history is going down, and the other is going up. Then when you calculated the entropy, then you'll find that the original, shall we say, canonical down page curve, which is a isosceles triangle, as we saw in the earlier pages. Now you find that although information is indeed preserved towards the end, the page time, nevertheless, let me first say, the page curves appears to be skewed, and the peak it tends to shift towards the end, and the reason for having three curves is that this statement is actually initial black hole mass dependent, and in here the red corresponds to whatever unit, 50, 10, and 3. So indeed, the skewness has to do with the initial mass, and so that's why we plot it this way. And so the punchline here for this page is that the famous page curve appears to have to be modified in order to be consistent. And this is after including the gravity effects. All right, now, so let me spend one page to give a few comments for those who are familiar with string theory and the replica wormholes, islands ideas. The one important, okay, first let's comment about commonality. The string-based islands approach And our approach, we based our approach on Euclidean quantum gravity. Shares two essential features. One, there exists more than two contributions to the evolution of the entanglement entropy. It's not just us who made such a conjecture. The islands conjecture also has the same starting point. Okay, and one is dominant at early time and the other late time. So this part is common between our approach and the string-based approach. And the second common feature is that the final entanglement entropy is dominated by the late time condition. This, by the way, is as well as they're common between the two approach. It is to me, it's almost kind of, how shall I say, almost guaranteed, because if you insist on preserving unitarity, this is probably inevitable. Now, this is also analogous in spirit to the so-called quantum extremal surface and computations of black holes. But however, there is one important difference between the two approaches. In the QES computation, the entanglement entropy is actually based on density matrix instead of quantum states. For all of us who were familiar with quantum mechanics or quantum field theory, I think we know what this means. So our view is that quantum states are more basic or more fundamental than density matrix. Dealing with density matrix, you don't necessarily need to know the in and out states. They're the matrix there, density matrix elements. So we feel that there's, let me restate. This is what we found that to be the difference. Okay, and indeed, as we all know, quantum states is the is what the standard quantum field theory based, right? And so I hope this comment makes sense to you. And with the remaining 15 minutes, let me introduce to you an idea, a suggestion on how we may possibly break away from these pure theoretical debates. And perhaps just because it's purely theoretical debates, that it lasted for more than 4 decades. Physics is an experimental science, and without evidences, and then we'll just keep debating. So,
Sorry, can I ask a question?
Yes.
Regarding your computation of the page curve, or let's say the entropy curve that you showed before, can you also repeat the same computation with a Lorentzian path integral and get, let's say, an equivalent result?
Without path integral,
with a Lorentzian path integral, like just with without going to Euclidean path integral, by using some
stay with the Lorentzian.
Yeah.
Well, we didn't do it. I don't think you can do it. I do not even know how to cross from one history to another. If you are staying with the Lorentzian space-time, then you will have to have I think, full-blown quantum gravity theory in our normal sense, like our flat space-time quantum field theory, which is lacking. Yeah. I think this is also perhaps why Hartle and Hawking jumped to the Euclidean space-time and play with it, and then transforming it back. Yeah. By the way, yeah, good to talk to you. I know you're talking with Sasaki-san and so on. Yeah, we
indeed.
also
Nice to see you again.
Right. Very good. Okay, now, so without further ado, let me motivate you why we need to do an experiment. So mostly theoretical, I already said. Now, how about just go directly to like, oh, astrophysicists are dead. Let's look into the sky. But the trouble is that astrophysical black holes, with this, solar size, of course, one solar mass cannot form a black hole, but several, let's say 3 and above. Now, if you leave such a black hole isolated in the universe and let it evaporate in a Hawking way, how long does it take? It takes 10 to the 67 years. Yet our universe is only 10 to the 10 years old. Now, so in comparison, this is like, the first split of a second of a baby. It's too junior, too young. Temperature is too low. Now, I hope you share my view that, or many others view that, what's important about this whole business is towards the end life of the Hawking radiation, or black hole evaporation. How this happens, or how this happens. But not here. Here, it doesn't tell you much. But that's the situation. We need to wait until I don't know when to see the end. And so this is already one big issue, unless we have some primordial black holes, which is small enough that after 10 to the 10 years, it's almost the end. There's been people considering that, but there's no concrete evidences nor predictions. You don't even know when such an event will happen. How do you search for it? And so this is kind of an inherent difficulty. And I also like to say, to my knowledge, this is perhaps the first time in the history of physics where you have some very important fundamental topic or subject, which in principle has no direct evidence or observations. This is quite a quite an interesting challenge, and that is why I think people started looking forward to studying it with some, and how should I say, with some physical system that can mimic the black hole evaporation physics, only that part, but not truly a physical black hole. Let's call it analog black holes. And Bill Unruh was the first one to make this such a suggestion with sound waves in a moving fluids, what he himself called this dump holes. And this, the sound wave plays the role of like photons or gravitons. And there, in this system, there is indeed a horizon. Now, let me not, I don't have the time to, explain to you the details. And there are subsequently, there are various ideas. Traveling index of refraction in the media, violent acceleration of electrons by laser. This is by Tajima and myself, and then electromagnetic waveguides by Unruh and Schutzheld, and then Jeff Steinhauer has in the past 10 years has performed a series of experiments in Israel using Bose-Einstein condensate as the fluid. So this is basically, conceptually, this is following Unruh's idea, but technically is using something much better controllable. Bose-Einstein condensate with very interesting results. Now, it's been long recognized, and in many textbooks, such as the well-known Brill and Davis book on quantum field theory in curved space, and other books where there are dedicated chapters talking about accelerating mirror, typically just 1+1 dimension, and show that actually such a system, by interacting with the flat space-time vacuum fluctuations, has the physical properties that has almost one-to-one correspondence to the black hole evaporation. Now, as early as 1976, Fulling and Davies looking into this, inspired by Hawking's work on the black hole evaporation. Then Davies, Fulling, Unruh, Wilczek, as I just now mentioned, Carlis Wiley, and Hotashutsu Unruh. Then in 2017 and 2020, I collaborated with Gerard Mourou, the 2018 Nobel Physics laureate. He's a laser expert, so we made a suggestion on how to create such a analog flying mirror as an analog black hole. By the way, this let me make a quick comment. Among these, theoretically, I think accelerating mirror that deals with interaction, interplays between this mirror and the vacuum fluctuations. I personally feel that comes the closest to the physics of a true black hole Hawking evaporation, whereas the acoustic analog is relying on sound waves, and that is a collective mode of the fluid, of the medium. It's not, I think the plus is that this type of approach is taking advantage of or drawing analogy, let's say, between we many of us like to say Einstein's general relativity tells us that space-time is like a fluid, or all the stars are dust, kind of a non-interacting fluids, etc. So from there you can have some imaginations, but as far as the Hawking effect is concerned, I feel that accelerating mirror is the one that goes the closest to the real physics. And the challenge or the question is, how do you realize that physically? So this is what Mourou and I did. So a flying mirror, just 1+1 dimension, and you imagine there's a mirror, and at some point t=0 suddenly decides to move, and not only moving but accelerate, and asymptotically it's approaching the null rate here, 45 degrees, and if you suddenly decide to stop the mirror flying, so it stops, and then its whirl line now starts to go straight up. So this is I can even perhaps make a thicker line down here. Perhaps I should have done that. So this is the whirl line of the flying mirror. Imagine surrounding it, there's always incessant, vacuum fluctuation of pairs. Then there can be just like this one. You can imagine there can be fluctuations where both particles, never hit the mirror and they remerge into nothing, as the Heisenberg principle requires. But there can also be the cases where one hits the mirror and got reflected, whereas the other one just happens to move along with this null rate, and this acts like an effective event horizon. And so this is kind of attached to the horizon until the end, whether it's kind of a sudden stop or the mirror just disappears or something, then there they can be released. And Now, but their entanglement still remains. So that red dot and this blue dot, they're still entangled. So if you are able to create such a mirror, and you can try to observe the entanglement between, Hawking evaporation, which is going towards the positive X direction. Oh, by the way, the mirror in this drawing is moving towards the negative X direction. Therefore, these Hawking particles, upon reflection, they suffer a Doppler redshift. Whereas the partner particle, if not, is kind of attaching to the mirror but never reflected. And by the time when they're finally released, their energy remains to be the original. So there is a question by Igor. So Igor, please. Hello? We cannot hear you. Igor?
Maybe you have to unmute.
Oh, I have to unmute. All right. Have I done it yet? I don't know how to unmute you. Just a second, huh?
We do not hear you.
Can you hear me?
Yeah, we can hear you now.
Okay, thank you very much. But I can
Sure.
wait until you finish your talk.
Okay. All right. That's good. Thank you very much. Yeah. So, all right. So let me add that this Doppler redshift, where the Hawking particle is moving backward against the traveling mirror, is this Doppler redshift is mimicking the severe gravitational redshift when the Hawking particle is trying to leave the black hole event horizon. There's a very deep gravitational potential because gravity has very, huge space-time distortion. So there's so this is the way we try to study black hole Hawking effects in the laboratory. Just now I mentioned the work by Davies, Fulling, and Aru. They, in 1976, computed the energy flux of coming out from an accelerating flying mirror, and they show that indeed it's positive definite, meaning indeed there will be some radiation coming out. Now, but okay. The additional question is then, knowing that there are indeed radiation coming out from a flying mirror, are there going to be entanglement? And that credit belongs to Wilczek. He was the first one, to my knowledge, to suggest that the answer to the information paradox lies in the entanglement between Hawking particle and its partners. Now, one can, in principle, also study the evolution of the entropy of this flying mirror system based on different mirror trajectories. Different ones can, in principle, give you different scenarios of black hole evaporation. I think I unfortunately run out of my time. Could you please give me a second? Now, so let me quickly say how I managed to make this conception. There is something called plasma wake field acceleration, originally proposed by Tajima and Dawson in 1979. They proposed to use a laser pulse injected into a initially quiescent plasma. This is all moving to the left. And through the interaction of the electromagnetic fields of the laser with the plasma's back reaction will be some kind of oscillation. which we call plasma wake field. The idea, the hope is, oh, by the way, plasma is being already ionized. There, if you manage to separate ions and electrons temporarily, like what this is doing, then the field amplitude can be 1,000 to 10,000 times higher than the conventional, fields in the conventional accelerators, such as the LHC at CERN and so on. And so this lies the hope for the future. If you want to study higher and higher energy physics, then 6 years later, I with Dawson was we are postdocs of Dawson separately, and we proposed another idea. We replaced the laser by a high energy electron or positron or proton charged particle beam, and we showed theoretically equally strong plasma wake fields can be excited. And the idea is like surfers in an ocean wave. You should, if you injected another clump of particles, say electron or positron or proton, then by riding on this wave, they can gain energy. All right, this is the way, this is the concept of acceleration. Now, what's that to do with what our analog black hole? Now, sorry, one more sentence. If the perturbation of the plasma is linear, kind of not so big, so this is kind of a sinusoidal, beautiful looking waves. However, if the laser pulse or electron beam gets more and more intense, so intense so that the perturbation to the plasma is becoming nonlinear, then what happens is that this is a laser pulse and that it moves to its left, like here. Then it tends to expel all electrons behind it, around it, until it really goes away from the region that the electron finally has the chance of rushing back, attracted by the less mobile ions left behind. So there's kind of an ion bubble, shall we say, and that manages to attract the electrons back. But having the electrons all expelled, so the wave is broken, we call it wave breaking, then when it rushes back, it is in such an exodus. I mean, it's becoming almost like a delta function density here, which can serve as a mirror. And by the way, this whole thing moves together with the laser pulse, so it is near the speed of light. Laser traveling in a medium is slightly less than its speed in vacuum, but still very close to speed of light. So this piece of mirror, by birth, is a flying relativistic mirror. And so that's kind of what we were trying to use. By the way, plasma wake field is very easy to appreciate. The mother duck, when you see in the lake, and a lot of ducklings behind, and they are separated in almost equal space. That was because they knew how to take advantage of their mother. They all ride on the crest of the wave, of the wake, that the mother try hard to spend energy to create. And they can ride on it without spending much energy. They are accelerated in a sense. All right, so this is the plasma wake field. Now, so in the nonlinear regime, as I have just said, the wake field is almost like a tsunami, all piled up. Sometimes you can even see the bottom of the ocean. Oh, by the way, so this is self-propaganda. I feel very honored to have been awarded with this year's Hannes Alphen Prize by the European Physical Society for my invention of the plasma wake field acceleration. I mean, for this idea. So I tend to know a little bit about this thing. And also, this I already mentioned. And if you send a pulse of optical laser shooting onto this plasma mirror, which is after all a plasma wake field in its extreme, and by reflection, you can turn the optical frequency into X-ray. This is a Doppler blue shift. So this can indeed serve as a mirror. This is a computer simulation. So here's my. So here is a kind of a analogy, a cartoon to draw analogy between a true Hawking effect with a laser, with a black hole, and if you like, you can evoke Einstein's equivalent principle. Imagine that this piece of mirror is a tiny pixel of the surface of the black hole with a constant acceleration a versus g. Now, so you can necessarily, easily imagine the Hawking temperature in this case is proportional to this g or a, as we remember in the first slide that I showed you. So they are flying backwards on this Hawking radiation, suffering, as I said, the Doppler redshift. Whereas in this case, these, at infinity, when we observe, these Hawking radiation suffers severely the gravitational redshift by climbing out the very deep potential well, gravitational potential well surrounding the event horizon. As we all also know well, that at a distance, when you look at in our rest frame, the infalling partner particles has severe time dilation. So they're almost not moving. They're just sticking to the event horizon, pretty much like here. All right, so these are the ideas. Oh, well, Gerard Moore gets the Nobel Prize. So let me know. So how do you make it accelerate? It's quite easy, because we know that light traveling in medium has an index of refraction that's not equal to 1. It is slightly less than 1 because of the plasma effect. And this is well known. We all learned this from Jackson's book. Now, so you can imagine if you tailor the target density such that it's dense at the beginning and gradually gets more and more dilute, then your laser pulse, which creates a mirror behind it, which is tucked behind and dragged by this laser forward, and this laser can get faster and faster because the index of refraction is getting more and more approaching 1, approaching unity. So this mirror can accelerate, and different mirror trajectory. I mean, how it accelerates can tell you different scenarios of Hawking evaporation. And the Hawking radiation, of course, as I already said, is moving backwards. These details, let me skip. Basically, I need to say, imagine if you tailor your target density in a constant plus Gaussian type of form, then asymptotically its trajectory will asymptotically approach the Davis-Fooling trajectory, which is associated, which can give us a Hawking temperature, which is inversely proportional to this capital D, where D is here. It's kind of the variant or the standard deviation of the Gaussian distribution. And so, so 5 years ago, 6 years ago, after publishing that paper, I launched a international collaboration, analog black hole evaporation via lasers, with the acronym ANNABEL. And this involves French collaborators, Taiwanese, and Japan, Kansai Photon Science Institute. And time is really, I'm really taking too much time. And so let me not prolong, but just said last summer, we have performed our first round of experiment in Kyoto. And our next attempt is to carry out a full-scale experiment at the newly built Apollon laser in France. This is on the Saclay Plateau. By the way, this is my own building, and this is a schematic layout of how we do it. And I think let me end here. I mean, these are the status. Let's not worry about. So basically, I like to re-emphasize that the information loss paradox is one of the fundamental problems in physics, but direct observation of black hole end stage is unlikely. Quantum entanglement may reveal the secret. Now, among all the analog black hole concepts, flying mirrors comes closest to the physics of true black holes. And then accelerating plasma mirrors may serve to address these some aspects. Of course, now some aspects of this paradox experimentally. And then this Annabelle experiment is in good progress. Thank you very much.
Okay, thank you very much for your very interesting talk. Questions, please.
Can I ask?
Okay, Igor, ask your questions. Are you on
Thank you
mute?
very much for the nice talk. Especially, I like your remark that physics is an experimental science. So I wish you a good luck with experiments. I have two remarks about the page curve. First remark, it seems it contradicts to unitarity, because unitary evolution means you should have zero entropy all the time, not only in the beginning and the end. This is first remark. Second remark is that page curve goes to the complete evaporation. It's already we discussed with you. What do you think?
Yeah. Now, this is a very interesting comment, and I will remember it and like to think more about. So let me be careful not to jump into any agreement or disagreement. As a continuing physical process, you insist that at every moment the unitarity must be preserved.
Yes.
And your comment is that in this case, in the page curve, except the beginning and the final points, the rest is not concerned.
Yes.
Okay, let me think about it. Okay, I cannot answer you right away. But again, I think I already partially answered you about this end life thing, and I try very hard not to put my own prejudice into this talk. My own prejudice is that black hole evaporation indeed cannot evaporate entirely away, and must leave a remnant at the Planck size. This is based on generalized uncertainty principle. Like the history of physics that had taught us. Let's say the history of quantum mechanics. The final form of quantum mechanics by Heisenberg and Schrödinger is around 1925. But during the first quarter of the last century, there were so many important discoveries about quantum mechanics without having the final form of quantum mechanics. And how was that achieved? Either photoelectric effect or Bohr's atom, or many things. I think it is because before you have a final theory, you can still make important discoveries if you rightly capture the essence of that final theory. Some principles, some symmetry principles, some guiding principles. And in this case, this generalized uncertainty principle, which can be argued without invoking string theory or whatever, just based on general relativity and quantum mechanics, but is also supported by the notions of string theory and even loop quantum gravity. So this generalized uncertainty principle, which combines the gravity effects into the Heisenberg principle, I think will survive in the day eventually when a full-blown quantum theory of gravity was matured. And so based on this, and by invoking the generalized uncertainty principle and following Hawking's own argument about his evaporation, we came to the conclusion that there should be a remnant. Having that, it's indeed like what you were saying, opens the door of many other possibilities about the solution to information paradox. Now, since there are other quite some questions, let's move on. So, Irina,
can I question?
Yes.
So you mentioned at one point that the calculation using the quantum state is more fundamental in some sense than the quantum the density matrix calculation. So could you clarify like what you meant by more fundamental?
More fundamental, yeah. Fundamental may not be the right word. It's more. What's the right word? Remember, usually in quantum field theory, we play with our formulation, our construction of the theory is based on quantum states.
Right.
You annihilate, you created this and that. Started with a vacuum state.
Yes.
Now, so density matrix is shall we say, a consequence. You carry out your calculations, and you have a well-described Hamiltonians and so on. Then you come up with your density matrix, and from there you can subscribe the probability of this and that, or transition amplitudes as such. But by jumping directly or starting from density matrix, instead of starting from the quantum states, to me it's less transparent. We don't know what was its basis. With this, do you see my point?
Right, but at the end of the day, the two will give the same description, right? I mean, although we do not know what the state is from which the density matrix comes, but we should expect equivalent description out of the two.
Yeah. If in the end of the day, maybe. I only say maybe because I cannot quickly come up with a counterexample, but you may be able to imagine the following, where let's think back to 100 years ago, quantum mechanics. Maybe there are physical cases where if you start from the quantum states, and then you will be safe to it would be safe to carry you all the way to the end of your answer. Whereas if you start from the density matrix, I am a bit worried whether in some cases you may not be able to go all the way to the end. Sorry that I cannot come up right away with an example, but I'm just.
The question was mainly based from the intuition we have in quantum mechanics. So in quantum mechanics, the two give the equivalent description. But your point is like we do not know where the density matrix comes from in this case, in this computation for black holes. What's the underlying states per se? You are worried that something may be more transparent in the state description rather than in the density matrix.
That's right.
But I understand. Okay, thanks.
That's right. Sure. Yeah. Now,
I see the next question from Timofey Rusalov. Timofey, please ask your question.
First of all, thank you very much for a great talk. I have two questions about page curve. The first is the following. Is it true that the problem of information loss arises when the entanglement entropy of Hawking radiation begins to exceed the Bekenstein entropy of black hole after page time.
You mean here?
Yes, yes, yes.
It's a little bit more subtle than this. Actually, you know what? Ironically, once it passed this half time, the page time, it's moving. That the whole evolution is towards the restoration. Let's call, instead of preserving, to the restoration of the unitary. It is actually not the beginning of losing or seeing the sign of losing information. Information, let me come back to here. When you are at around here, the information actually is gradually, restored. Of course, before you come to the end, you're not very sure yet. But here, the tendency is clear. Okay.
Okay. My second question is the fact that the entanglement entropy of Hawking radiation follows the page curve a sufficient condition for evolution to be unitary, or only necessary condition?
Would you please repeat again?
Is the fact that the entanglement entropy of Hawking radiation follows page curve a sufficient condition for evolution to be unitary, or only necessary condition for unitary evolution?
Good question. This, by the way, if you look back to the 1993 page paper, it's very mathematical. So it's a equal sign everywhere. So I would imagine that this is both sufficient and necessary condition. If your information goes this way, then your entanglement entropy goes this way, because you can, step by step trace it backward. If your entanglement entropy indeed goes up and down like this, then by this definition, your information goes in this yellow curve in this way. So from that angle, I tend to think that this is both sufficient and necessary, but I cannot say for sure here. I'm happy to think more about it.
Thank you.
Sure, thanks.
Okay, more questions, please. Okay. If there is no more questions, let's thank Pisin once again for his interesting talk. Thank you very much. Okay.
Thank you.
Thank you very much, Pisin.
Thank you.
Thank you.
Thank you.
All right. Sure, thank you.
Thank
We'll
you.
see you again in Shanghai.
Bye-bye.
Bye-bye.
Bye-bye. Bye-bye.
Bye.
I'm leaving. Bye-bye.
And it would be great if you will send slides with your talk. And I will upload
Okay.
them.
I'll do that. Thank you for the invitation again, Alexei. Okay, bye-bye. Good night.
You're
It's
welcome.
late on my side.
Yeah,
Bye.
indeed.
Bye.
Yeah. Hi, Luca.
Hey, Alex.
Do we still have something to discuss? Because I
Yes.
remember we wanted to discuss something before, but looks
Yeah,
like
but
you
I was late.
giving very intense talk.
I was late, yeah. I don't know if Sravan is around. We can organize a bit the program, what to do next. But yeah, I don't know. I see Sravan online. I don't know if he's around.
I also don't know where he is.
But if it's too late there, we can just
Yeah,
postpone.
it's kind of 11:30.
I know. Come on, it's still before midnight.
Yeah. Yes, it depends. But tomorrow I have a lecture also.
Yeah, sure. But anyway, yeah, we can do it maybe next. When is the next one?
Yes, sure, we can do it. We can choose some. Well, practically maybe next Thursday we can do it. We have no seminar, but we can still gather at the same time and discuss.
For me, it's fine. Next means, yeah, sure. I think it's fine for me.
Next means 19.
19th, yeah. Yeah.
Bye, everybody.
Bye.
Bye-bye.
I actually have to carry on.
Okay, then let's do it next Thursday.
Yeah, let's do it because today is indeed kind of 11:30. It's not the most brilliant. Yeah.
Yeah. So regarding speakers, we need to only cover one for December, right?
No, but it's kind of found because I met Miss South a second.
He
told
said
me,
yes.
Yes, but he's
Okay.
very open guy. He just told me that before. Actually, I just have to say I still have to send him a mail with possible dates, but I'm sure that one of these Thursdays in December will be used by him. So it's okay.
Mhm. Okay.
The only thing which we'll have to do is to shift a little bit earlier the start because for him in Japan, it's too much.
Yeah, it would be 1 hour more, right? Compared to
Yeah. Well, I don't know. Also, there will be soon the shift in Europe, this daylight.
Yeah, it means we can do a three Central European.
Japan and Europe.
Mhm.
7 hours, it will become 8 hours.
Yeah, we can do a 3 maybe. 3 p.m.
Yeah, or maybe even at 2 by the way, because he told me clearly that he doesn't want to start after 10.
Okay, I see. Well, we
Seems
can
to be
do
very
it.
logic demand, He is active guy, well, very much active, but still start after 10 is already too much.
Okay, man. Yeah, okay, yeah. So let's discuss
Yeah,
maybe next
sure.
week. Anyway,
Sure.
we keep in touch on WhatsApp. Okay.
Okay.
I think Zravan just went somewhere. I don't know. He's not
Yeah,
there.
maybe. Well, then see you later.
Okay,
Next
well,
week.
have a nice evening. Bye bye.
Sure. Bye.